So he came in and fixed it up for us, the service agent from Melbourne, and he helps us out if we have any. If I can't answer a question, then I can go to Steve Shammer, the service agent for TGA Instruments, and he can answer it for us. So hence you get charged about $5 an hour to use on ACLS. Safety wise, just be careful cleaning the crucible with a blowtorch. There's an image of it there where you get your fingers back here and the flame is there. So just be careful of that. So there's no protective equipment required for the lab. I look after the lab and the instrument, and when I'm away, my colleagues Ladge and Mohan can help you there to my technical officer colleagues. Resources, there's good manuals on here. TGA Instruments has also an excellent YouTube channel. They also have online webinars, and I'll send you links to those after the training.
Thanks.
The network name has just changed. I'm not quite sure what it is now. The files that we store are on a network drive here, and you can look it up from your computer at IFN. I'm not quite sure whether you can at the School of Medicine.
What's the network called?
It's changed at the moment, so let's have a look.
Probably we could probably map out my computer for it, probably.
So looking here, and it doesn't seem to be many computers. Oh, yeah, there's 4 here. There's normally about 200 on here. Oh yeah, they're coming. There's 16 now. So, and this one used to be called that, but now it's changed. So I'll sort that out next time I do a revision. Oh, here they all are. So there's various computers. The XRD computer is on here, and a bit further down. So you can access your data from this computer because the drive is networked.
Yeah. So the network's just in the IFM computer to get your data?
Yep.
And the computers in this lab, is there no USB policy or USB is allowed?
USB is allowed. Yep. Because the older ones we can't get data off. That one isn't networked, and that's about the other. That one's networked.
Yep.
And that one's networked. So these 3 are there's a Q50, the Q200, the Q20 next door. There's a high temperature DSC. So there's that DSC. That DSC goes up to 725, and that STA goes up to 1600. So it's a DSC TGA combined. But these 3 instruments, that's 4. This one, there's one in that room, and the DMA that normally sits there, it's out. It started to, who was to do carbon fibre, it used to start to smell, so we put it in another area for the time being before we get snorkels put in here to take that smell away. Yes, it's gone in, and they all use the same software. The Q series use the same software, so you'll find that they use the DSC, it's the same software as this one. So calibration, how do you know results are precise? Will your results be comparable with other TGA instruments? You can be rest assured that the instrument is calibrated regularly for weight with samples, with little calibrated samples here. So I put those in there and tell the instrument that we've got a 100 milligram weights and a 1 gram weight, which is the maximum you can have. So I calibrate the instrument using this for weight, and for temperature it's slightly unusual that we calibrate it for temperature using the Curie point of nickel. These are small nickel samples, and I put one of those in there, and even though they melt at a very high temperature, about 11 or 1200, they change from magnetic to non-magnetic at 300 degrees.
Okay.
So during that point,
what was that point you mentioned? Curie point?
Curie point, as in Madame Curie, C-U-R-I-E.
Yes. What's it? Sorry, I'm not too familiar with that term. What's the Curie point for?
Is the change for a steel, Curie point is when it changes from magnetic to non-magnetic.
Oh, okay.
For normal steel, it's quite high, but for nickel, unusually it's quite low for a steel, 300 degrees. So we put a sample on the pan, we align it this way. So the pole or the magnets lines up. We put the, oh sorry, wrong one. No, we put a sample on there, but there's no, I can press stop. So press furnace, that's the one I wanted, and this will lift the furnace up. So I have some control, basic control of this bit there. And I have a big magnet in here that I put underneath there, right at the base, and when the sample is heating up, it's having an effect on the magnetised nickel sample. When that becomes non-magnetic at around 300 degrees, it lifts up, and there's an apparent weight change, but it's not. It's just a change in magnetism.
Oh, okay.
So we use that to calibrate the instrument at a good midpoint around 300 degrees.
Pretty cool.
Yeah, it is. It's unusual that such a high temperature metal has a low temperature Curie point. To reverse that, I can press it again. So I've logged onto the computer with my own Deacon username and password. Open the TGA Explorer shortcut. Just here. It's not open. It's in fact it's not. It's normally this shortcut is normally on there, so I might have to. So the network on my profile hasn't come across. So just open this to gain access to the instrument software. Yep. And so I can control the instrument. So ignore the error that pops up about evaluation. There we go, it's right on time.
Cool.
And the instrument is now ready to use.
Okay.
Ensure your crucible is clean and dry. And this, I cleaned it before. Place it on the crucible holder. So I use the tweezers so I don't put dirt or oil from my fingers on the crucible. And I can put on here like that. There's the hang down wires that go underneath, go in this screw, in this slot here. It's like a, let's put it like that. I use the steady rest here to steady my hand. And I can put it across. I'm going to press this one here, tear. And when I do that, this hang down wire will drop down and this will go across, load it up. And it will zero this.
Zero up.
Yes.
Cool.
We'll lift it up. So that's where there's a hang down wire that goes all the way down to here, and on the other side is a smaller one with the same, but a lot cleaner crucible holder. So that will lift up, and this the value here was, it's pretty close to zero already. It will go at zero, then it'll be ready for me to put a sample on.
So you said there's another one inside here.
Yep.
Does that act as like a counterbalance?
Yes. Yeah, it acts as both of those now. One of them just has a longer platinum wire hanging down. It's like a beam gun. It's like the scales of justice in there. It's like one on one side. Yep. So, yep, press tear. I've done that. Now, yes, tear. Yep, the nasal sample here correctly. So it normally takes about 1 to 2 minutes to tear. So I'm going to get a sample, about 5 to 10 milligrams of sample, and prepare that in the meantime. The sample I'm going to use today is some paper.
Paper.
It's good because it will burn. It's a fine tweezers, but some scissors. You got scissors over here, James?
Scissors.
There'll be some of my tools.
There's scissors here.
Scissors here.
Cut a piece of paper, and I'm just going to cut the corners of them to make sure it sits in my pan, sits in the crucible. So just make sure they don't overlap. to
You fit the crucible properly.
yes.
Okay.
I'll take it now. That's my crucible coming out, and I don't want that paper to overlap the or to lie over the edge, because any gases coming up will make this float a little bit, and I'll get a little bit of a bumpy curve or a noisy curve. So I want to make sure that my sample doesn't hang over the edge. Okay. And I can take it off and put it down to put my sample in, or I can just put it in here like that. And that's what I don't want. So I don't want it to sit on the edge. I want it to sit completely in. Okay. I can make sure. There we go. I just picked it up and dropped it a couple of times, just to make sure it's sitting at the base. I'm going to press sample, and that will hang down wire will drop down, and the sample will go in. I can control it the same way here. I can go control, sample, load and unload here. Likewise, I can tear it here. Oh, furnace up and down here. Tear is not on there, but I can tear it via here. This one, tear. Is that on the is it on the tools? Experimental. No, it's on the calibrator. So that's my sampling, and we're going to heat this sample up to 600 degrees. I'm going to heat it up in nitrogen, which is gas 1. Then we're going to swap it over to gas 2 at 500 degrees and see if it can bust anymore. See if the paper will burn around 300 degrees. And if we introduce air into it, it should burn some more because air has 20% oxygen. So I've loaded my sample, place it on there. And my sample weight, so it'll show up here. My sample weight is 2.81 milligrams. It says here 5 to 10, so I should put a little bit more. Oh, that's what happened. It's, someone's put the username is lecturer and the password is lecturer. That's I probably should rub that out because that's a generic one. And if everyone uses that, then you don't have a network drive, so and you can't store your data to your home drive. So the first thing I'll put down here will be the dates. So
13.
Thank you. 19. Right. 336 is the test number, and material is paper. And it's 2.8 milligrams. It will start to decompose around 300 degrees, say 350. I'm going to heat up to 600 at 20 degrees per minute.
Well, if you're not sure of decomposing temperature.
Yep. You should have some idea. You can go 100, 200 degrees. It's not good to put a low temperature. Some people do it, so their decomposition temperature is 240 here. Why go to 650? They often have a big flat line. The sample just keeps on going flat, and it just wastes a bit of time. So I'm not quite sure why people go up there. But no one's gone up to 1,000, which is good.
So the decomp temperature, just search the literature for a ballpark figure?
Yes. And you can always increase it. I'll show you that in the testing.
No problem.
So we're up to the next page. A standard test, ensure the gas flow is correct, and it's 40 and 60. I'll put that in because some people change it, but don't change it back. open the experimental wizard from the menu bar. So it's this one here. And 95% of people just do a ramp. But you can do a ramp and switch the gases over. That's what we'll do today, just to show you that you can do things a bit more advanced. You can heat it up and hold it for, say, oxidization tests, and you can heat it up in steps. But this template we'll use today, the TGA ramp, and switch the gases. So we're going to heat it at 20 degrees per minute. We're going to heat it up to 600 degrees, and we're going to swap the gases over at 500 degrees. I think this is just a sampling rate, and it's normally 0.5. This is the post-test conditions, and it's normally open and unload and air cool for 10 minutes. So it'll open the furnace, unload the sample, and it'll cool the furnace down for 10 minutes. So that's all quite standard.
Sorry, to get to all that, it was just this wizard hat, yeah?
Yep. So cancel that. Yep. This one. Yep. This one here. There's 4 methods or 4 templates here we can use. I'll show you the second one. Most people just use the first one here.
Yeah.
And that hasn't quite remained the same, so I'll go to 600 for the final temperature. We'll swap over the gases at 500. This I showed you what they were. My method will come up here with my parameters. I'll put my sample name, which is paper. I'll say GS and say September. Gas switch, September. And I'll store it in my TGA folder here. And how far is Rob away? It should be there. Yep. And here's all my other paper, GS. August was the last one I did, so I did this training in August and then I did it in September. And that's my file name. Looks like that's still the network name. I was told that network name had changed, so it looks like it's still the same. So there's a network drive there, but I thought it changed. Change that to Rob. So when I get the file generated, it'll have my name at the top report that I was the operator. And I'm going to initially do this sample in air. In nitrogen, and it'll change to air later. So the balance always has nitrogen up in here to protect it from the fumes and the smoke that comes off the paper. And the sample will have nitrogen on it too. But we can change that to air. We can change it to, what other gases are? Argon. We can hook up to it pretty easily. This one, it's sitting free as argon, so people who use this for some of the low temperature metals, like indium and tin and zinc and aluminium, magnesium, can do their sample under argon, which is a more protective atmosphere for metals. We can start this run here. We've got to tear it again.
Just a quick question. Back there it had 60 for the flow rate. It had 60
milliliters.
Yeah, per minute. Is that a regular flow rate? Is that the suggested one?
Yes. Some people change it. They want to minimise that, or they want to promote oxygen. Don't want any. They change it. Unfortunately, they don't change it back. So it's one thing. One of the variables you need to keep an eye on. That's why I listed it in there. So we can start the run here, or we can finish. And Jake, we use that to start with, but you'll use that once or twice before you realise that all the information is in these 3 tabs.
Oh, okay.
Now we can change the procedure here. We can change the heating rate to 10 degrees per minute, which is quite normal, but we can't start the test until we apply that change. So now we can start.
Where do you say how many minutes you're going for?
In here, we don't have minutes, we have heating rate. And that's governed by, heating rate is Celsius per minute.
Oh, it's governed by the temperature.
1 hour.
Yes, so that should take about 1 hour, which is extrapolated there in the test it will take 60 minutes.
Yeah.
But what I did was I changed that heating rate to 10, then started the test. We actually want 20, so I made a deliberate mistake, which is unusual, but it does happen. I can change that back by right-clicking on here and modifying that running method. And that's the same for this one. You know, the DSC that you used and the DMA all have this feature where you can modify a running method.
Okay.
I'm going to change that back to 20. And send those changes.
So shorter time.
And it will halve.
Yeah.
It'll halve the time here.
So
Change to 20.
sorry.
Yep.
Does that restart it or just halfway through the run it'll change?
Yep, it'll change.
Oh.
Yep. It'll modify the running method. Unfortunately, it doesn't change it here. It changes it here and changes the time, but it doesn't change in that column. Maybe the next version will change it all.
Yeah.
So this is where you have to be careful not to bump the instrument. This will show up here. Well, that was the table. Yeah, so it's upset a little bit. The tables are separate to the other tables here, so make sure that we work on here, it doesn't upset that. We touch the instrument and all it has a worse thing. And shocking the door open just helps, because every time the door closes a little bit, this is the real-time graph. It doesn't get picked up on here just looking at it, but when you, I can show you, we can look at that graph in real time. I can open the analysis software here, or it's on the desktop, I thought it was. It used to be, but it's here. And if I open that test, September, should be the last one modified. Yeah, that's my graph at the moment, because it's a really small scale, 2 grams, and there I hit the machine here and hit it again there, and it's still, in technical terms, it's gone boing, and it's reverberating, I think is the technical term.
Instrument is very sensitive.
Yes, so you shouldn't touch it. Yeah, and if we put a sign on here, do not touch, more people touch it.
Really?
Yeah. It'll be a, yeah, it's one of those things that we try not to draw attention to something, or else it's like a wet paint sign. It draws people in. So you don't normally get that when I do this. It shows up on my graph, but you can cut this data off here. But it looks really bad. It hasn't settled down yet. I'll just go to, I think it's edits, graph, auto refresh data. Looks like it's on. So I haven't seen it refresh yet, but it looks like it's 55. So it'll refresh the data soon.
So, how did you get this whole graph up again?
Yep.
Sorry.
The easy way is exit in the control software. It's here.
Oh yeah.
Launch Windows UA.
Launch Windows UI.
Yes. And if I go to here and go to the manufacturer's website,
Can
So you-
download the
you can
software.
download that software. And that's the same software is used to analyze all the Q series machines. Universal Analysis 2000. If I
So
go
we can install the software on my laptop.
on your laptop, yep.
Cool.
TGA. This one. That's there. I actually, they're in, what it's called, they're in Delaware, in New York, in America. I went there for training.
Oh nice.
So I went there for the DMA training. And so this one's a pretty easy machine to use. So you can, it's just like any website, you get to support software downloads. There's a few ways of getting here. So sort software by software, or by instruments. And well, that was. And we just look at the, what are we using it? thermal analysis, and we're using the Q50, this one here, and it's the advanced software, and you can download that here. I think that's version 5 point something now. Yeah, 5.5. So it's, yeah. And our software here is only 4.5, so it is a loaded version of software.
Just a quick question, sorry if it's stupid.
No.
What's the point of this graph if we can then just get up this graph?
Yeah, just that's a real-time run graph. It just shows you what it's doing at the moment, but you can do the same. This one probably refreshes quicker. If you look at August, the last one I think. Okay. And you can see where I hit the machine over here, and it did settle down, but and this is our paper decomposition. I said 350, it's more around about 300. It starts to lose weight, so it starts to decompose. And that's what you want for your DSC machine. If you want to test this sample in the DSC, we'll do the onset of the decomposition. That's using this onset shortcut here. And it puts a line here, but I want to take that away from that bump. I can smooth that out, but it's very hard to get rid of that. It's a real time, it's like a bump, and it's not really noise, so it's very hard to get rid of that. I can cut it out of the data, that's the easiest way. And so I'm going to draw a baseline along here, along there, and see when the onset of the decomposition started. It says about 350, but I'm not happy with the way that this one drew the baseline. It hasn't really followed that along there. So I can adjust that. I can't really adjust that. I'm going to edit, delete the last result, and just do that again, and bring this one a bit further here. So it follows that a bit better, and say, it's about 4 degrees difference. But it's drawn a nice baseline here and there. So the decomposition of paper in nitrogen is 344 degrees. So if I was to test that in the DSC, I would not go near 3, I'd stop at 280. I'd stop at around here to ensure that the data I get is accurate, because the DSC doesn't have a balance. So you could test a sample. See, I knocked the table to the bottom of that one. The example will show you. Pretty tidy. So if I started with a sample this big, and it started to decompose, and I finished with a sample this big, that's doing all my data off that one. So the DSC doesn't know that my sample size has changed. So when you try and keep it, you don't decompose it, and if you do, you can determine that the DSC it goes all black, which is not good for other people's samples. So people who, person before us was doing elastomer, was doing rubber, and if she decomposed her sample in the DSC, that would then affect your sample. So we try not to go close to where it decomposes. And you can clearly get that off this graph.
Cool.
What you can also get...
Sorry, just a quick question. If you were working with something not like paper, say something that's in a solid form, but it could break down to a liquid form, would you get a similar sort of graph, or would the weight be kind of consistent because it's just changing states?
What you might see, I'll show you some different graphs. I'll show you one of a sample they give us to test. Examples. This one. I think it's calcium oxalate, and it has 3 transitions from 0 to 800 degrees. So this one might be where moisture burns off. boils off, sorry. This one might be a resin, this one might be the fibre that, so it has, well, in fact it's not a fibre, it's a calcium oxalate, so I'm not quite sure what's burning off at each of those steps. You can determine those when each of them starts and finishes and how much it lost. Carbon fibre, people will burn off the resin in the carbon fibre, knowing that carbon fibre will burn. I think the carbon burns or decomposes about 1800 degrees. Okay. So before that, everything must be the resin that burns off. So we can determine that by the same method here. So a little baseline here, and I'll draw this one about halfway up the slope. And so that started to decompose at 125 degrees. When did it finish? We can determine that by pressing this. Here and that one there, and we're looking for the bottom one, which is 166. So we know when it starts, we know when it stops, what percentage of the sample is lost, and we can determine that as well by the signal change here. So we put this one at the start, and this one, so the midpoint of this section, the first transition, it lost 30% of its weight. And repeat that all the way down. We can even do the total weight lost from here to there. Will be 64%. And similar with my paper sample, it does the same. It goes from a paper sample, all that's left at the end is ash, and the ash is very light. If you look closely at the paper sample, this one here from, hopefully this one works, so same testing, we show people that don't bump it. This would have been the door closing, this little bump. This is the decomposition. But before that, it lost weight. Here. It lost, we can measure that a little bit. Signal change from the start to about 150 degrees. To the midpoint here. How much weight did it lose? It lost 3% of its weight. And we would pinpoint that to moisture in the paper. So all paper has a bit of moisture, makes it tactile and easy to handle. But if you leave paper or a newspaper in your car on a hot day, you come back and it's very dry and crunchy. It's lost all its moisture. For this paper, it was about 3% of its moisture.
Just a quick question. So when you add all these percentages and measurements to the graph, can you then export the graph with those still on it?
Yes. So we can. What's the one before that had a bit of data on it?
Yep.
So I can file, export the data file, the file signals, file and the plot signals.
Oh, awesome.
Cool.
And select the file you want to send it as a spreadsheet text file, and press finish, and it'll send that file as a text file, and you can import that into Excel. I've got other examples here to show you. So some examples. We've got a noisy one here somewhere. Oh, this is the calibration I did. The last one modified. It was calibrated by the service guy just on Wednesday. It was. So he's done it this year, but I haven't. The last one I did. This is the nickel file. So this is I use the YouTube channel for TA Instruments, and they told me exactly what to do. I have a few settings in here. I have to make sure that when this finishes testing, the furnace doesn't come down because I've got the big magnet underneath there. So a few settings I need to adjust. I start this at 250 degrees because there's nickel, nothing happens to it before, nothing.
250.
Yes, nothing happens to it before 350. This has an apparent 6% weight loss, but it's not. It's when it goes from magnetic to non-magnetic, it lifts up. and I can do the, I press TG here, and I put in this, and it comes up, it's 356.58, and I plug that into the, it should, I think 356 is pretty close to being right. If I put that in the data here, calibrate temperature table, the observed value is 356.56 and the correct value is 356.86, so it's spot on for temperature. Here's my sample starting to decompose now. If you put my nose to that, I can smell a bit of paper burning off. I won't do that, but I know from experience, you just smell a little bit. This is going to heat up to 500 degrees, and it's going to change from nitrogen in there to air, with that little bit of 20% of oxygen.
Just with exporting of the file, you said that exports as a text file.
Yep.
So does that just give you all the number values and you re-plot it in Excel?
Yes.
In Excel?
Yeah.
Right.
I think maybe you can go to Excel straight away.
Cool.
So it's just a spreadsheet text file, but
Then copy and paste to
Yes.
Excel.
Yep. It'll have either, it'll be a CSV file, which of separated values, or it might just be in tabs.
Okay. But if it just goes into numerical format and you got to replot it, wouldn't you lose these kind of information when you export it?
I think it might come out. You can do the
Use
plots.
Origin.
I'm not sure.
Origin
Or you can export the
software.
plot. Yeah.
Oh, okay.
As a PDF.
Oh, okay.
That's
I
cool.
know that one's a bitmap.
Bitmap.
Dark colours like yes. So that's that one. So that's the analysis program you can get from, you can download that. That's all the calibration files I've done. Let's just look for another one here. TGA check. Maybe it's under my calibration.
Do we need to do the calibration before we
No, I
test?
do it.
Oh.
It's running pretty well. So this is her, that's a PDF file, which is, it's good to see what it does, export. There's the plots. Our IT people said they just updated it. Yeah.
Oh.
Yeah, that's
Cool.
good. That has put on, this is the weights, and it's also got a derivative curve here as well, and that amplifies the changes in where the inflection in the curves. So this one here is the inflection under that point where it started dipping down, so it started dipping up again. Normally we don't have that curve, but it can go on. And if you want to open that, not Caroline, I'll open up, I got to do a lot of work in here. Yep. So simple test, there's something like my paper, and all it's disappeared. Went from 100% down to next to nothing. I can tell you quickly how much it lost. And there, it disappeared. So it went, and
To ash.
yes. Oh, not even ash, because there was nothing left.
Nothing.
0.5% of its weight.
Even ash being
Ash will have a bit left.
decomposed.
Yeah. Well, but the points, I can't remember the point I was making now. That's not a bad test because everything started finished at 500 and 600 finished. You don't want to keep on going to 900 or 1,000. Each time it goes for 1,000 degrees, it just degrades a little bit. It's not. Now, I'm sure we can do it. We had a student who did it and held it at 1,000 for about 5 hours and it broke.
Oh
really?
my god.
So it's not designed for that. Oh yeah, that's. Oh, we're going to show you the derivative curve, weren't we? So open Vargos 7Z, was it? Yes. That
I
must
think
be
it was the one below that.
M1. And right click for signals. weights. Now I want the one on this side to be weights again, but at a derivative curve. I think it's the derivative time. Derivative curve. I'm not quite sure which one, but that shows you exactly when this curve starts sloping down to when it starts sloping up again. That's that point there. Apart from that, it's a pretty clean curve. We can smooth this out. There's a few bumps in here by going tools, smooth, or there's a smoothing function here. Put a smoothing factor of 2 in. Did I do that blue curve? I'm not quite sure.
Are these bumps knocks of the table?
I'd say so. Or the door closing.
Oh, sorry. How come there's a lot more clearer on this one and where here they don't seem very okay?
I'm not sure. Label things like that if you want to. And I'll take that derivative curve off, like signals, and just not using it. It's a little bit confusing sometimes. It's easy with a nice clean curve like that. And save. So I want to show you how to compare curves. So we do that by comparing. I'll use some of mine. So I'll use this one and that one. These two are similar curves. They go to 600, don't they? Yep. And you roughly said that my paper loses 20% of its weight. They look fairly similar, but we can test that. We can overlay the curves. Graph. Overlay. Yep, here it is. I just auto-config that and make sure it's got the same parameters, and it has. And you can put it on top. The only thing is you can't export both at the same time.
Wow.
We can do the graph, but you can't do both. And when we go to file, that option is grayed out. But you can compare graphs using this. And that's the software, that's a free download.
Yeah. Very useful.
Yes, it is. So we'll go back to our data, and that's
11 minutes.
Getting to 11 minutes. We say, do it now. Say, go to the next segment. And I'll just bump that across to the next segment. I just went right click, and I said, I want the gas to start now.
Can start.
And it will decompose a little bit more now that the oxygen is entering them.
Could you get the program to show you on the graph the exact point where the second gas kicks in?
I'm not sure. So if you want questions, just send me an email, and I'll ask the Melbourne guy. If he's not sure, he'll have to write back to the Delaware guys, and that takes a couple of days to get back to us.
No problem.
So that's immediate.
When you export all the stuff that tells you what user ran it and all that, does it give you these like time point info?
Let's have a look at some of them. Can you see on the network? Where's our data stored? I think it's in here. The D drive. So user data. Yep. Oh no, I don't think I can get into there because they're usernames. So you should be able to get into mine. Here we go. HP. No, it's the wrong one. I think it's this one. Yep. Let's see if anyone else has exported data. So that's not what we're looking for. TGA. So this test here.